Right. So we have finally finished one-dimensional motion, two-dimensional motion. We have already finished with the course of kinematics. Okay, so kinematics is done. Kinematics, we're already done with this thing. Okay. So this is second partial. Let's jump right into our third partial. Our third partial will be about another type of movement. Well, another study of movement called dynamics. And I don't know if you guys remembered, we already talked about the differences between dynamics and kinematics. Uh, but let's review them. It's very simple. It's a very simple concept. Kinematics has more to is related more to describing motion. Okay, so kinematics doesn't have to do anything with forces. Okay, kinematics is only about describing motion. And how do we describe motion with respect to time? Well, we have position with respect to time, we have velocity with respect to time, and we have acceleration with respect to time. These three variables that we used to work in kinematics, these three variables were describing how a particle or an object or whatever was moving through space with respect to time. Okay, so since we were relating everything with respect to time, we were describing the different types of motion. We saw one-dimensional motion, so horizontal and vertical. We saw two-dimensional motion, so horizontal plus vertical. And we saw another type of one-dimensional motion, circular. Okay, so we saw a lot. Okay, in this partial we saw a lot. We saw 5 different things, right? And all of these things we were only relating them to position, velocity, and time. Now, in dynamics, dynamics is something that doesn't describe motion per se, but it's something more of the study of the causes of motion. So it's a study of what causes motion. Okay, kinematics is going to answer the question how it's moving, and dynamics is going to answer the question of why it's moving. Okay, why is this thing moving? So this is the main difference between kinematics and dynamics. Kinematics describes motion, and dynamics is going to answer the question of what causes motion. This, in turn, has a lot to do with a concept that we'll look at this video called forces. Okay, dynamics are the foundation for classical mechanics. So this is classical mechanics. Okay, and dynamics is something that came afterwards the study of kinematics. Okay, kinematics, big kinematic fans were Galileo, for example, and using Galileo's work, Newton. Okay, Newton was the one that started working with dynamics. Okay, Newton was one of the first persons to actually describe why these things were moving the way they were moving. So causes of motion. Okay, so now let's go right into another concept, something that has to do a lot with kinematics, with the dynamics, and this concept is the concept of a force. So at this point, some of you, well, most of you must already know what a force is, right? We live in a mechanical world. We experiment mechanics every single day of our lives, okay? So we kind of already have an idea of what forces are. This idea is both good and bad. Good because we already know the concept, it's not foreign to us, but bad because we sometimes tend, due to our own experiences, we tend to have misconceptions about what things are actually. Okay, so for example, a force we normally experiment forces as pushes or pull. Okay, when we think of force, we normally think of something that pushes or something that pulls. And that is not necessarily true, okay? A force doesn't necessarily push and the force doesn't necessarily pull. A force, rather, is something more it's something more of an interaction, okay? It's more of an interaction between bodies, Okay, so one body can interact with another, and this is what basically we think of as push or pull. When two bodies interact with each other, they are either pushing themselves or pulling each other. But it can also be something, some sort of interaction between bodies and the environment. The environment. Okay, so not only bodies with bodies, so bodies versus bodies, but also bodies and the environment. Okay, normally when bodies and bodies interact with each other, these type of forces are called contact forces. And these ones, well, let's call them action, whoops, forces that act at a distance. Okay, so two different types of forces, two different types of interactions, but they are interactions nevertheless. So remember, it's not necessarily a push or pull thing, it's more of an interaction, how two things are interacting with each other, two bodies. So forces, and I'm going to write this, forces are normally, well, when we're talking about mechanical forces, we will be talking about them, we will be referring to them as an F with a little arrow. This arrow, once again, represents a vector quantity. Okay, and vector quantities, we have already seen this, have both magnitude and have direction. Why is this important? Why should a force have both magnitude and direction? Well, for example, let's say we have a box here. So this box, we say we're going to push this box. We're going to push with a force of, let's say, 100 kilograms force. Okay, so this is the magnitude of my force. The next thing that you should ask yourselves is, that, well, where am I going to apply this force? Because if I apply this force here, for example, and my box is, let's say, on the ground like this, if I apply my force here, that box isn't going anywhere, right? So if I apply 100 kilograms of force here, that body isn't moving whatsoever because there's a bigger body here that is opposing this movement. But this vector, this is vector 1, force 1, 100 kilograms, but in this direction, this vector is completely different to this one. Okay, so maybe 2, sorry. So maybe this one also has 100 kilograms of force, but now it's in this direction. That force will probably cause some sort of movement over here. Okay, so it's going to move. So that is why it's very, very important to specify the direction of our vector. It's very, very important because the direction is going to basically tell us in what direction probably that object, that mass, is going to move. Okay. So let me continue here. I hope what forces and why they are vectors is something that is super obvious to you guys. I'm just going to say something else, and then I'm going to quickly end this video. I don't want to spend too much time here. One of the things, one of the principles, so one of the important principles, one of the biggest important principles of forces is the principle of superposition. Superposition of forces. And this principle, what it says is that the sum of all forces, okay, is equal to my resultant force. Okay, and we kind of already saw this in vectors, okay? Let's say we have some particle here, and we apply a force in this direction, and we apply, sorry, a force, I'm going to change color, a force in that direction over here. So this is F1, and this is F2. So the principle of superposition of forces tells us that the resultant force, the resultant net force on an object is equal to the sum of all of the forces that are acting on that object. So the object, in the end, doesn't feel two individual forces, but it feels one resultant force that resultant force is, sorry for repeating myself, but that resultant force is the result of adding the forces. So let's graphically add these two vectors. So using the parallelogram rule, so something like that, and something like this. Okay, so this is probably where these two vectors cross each other. So we have something like that. So this is my resultant vector. So let's call this FR. So the principle of superposition, what it tells me is that if I have an object that has many different forces acting on it, okay, that object is going to only feel one resultant force. And that resultant force is equal to the addition of all of the forces that are acting on that object. So this object is exactly equal to this thing right here. Okay, this system is exactly equal to this thing right here. Okay, so we can add all of the forces that are acting on one object and simply state that there is a resultant force. And the resultant force is also a vector, right? Because it has both magnitude and it has some sort of direction as well. So this is the principle of superposition. The resultant net force on an object is equal to the sum of all forces. So this might seem a bit, let's say, obvious to you guys, but let's see how we can work this with this thing if we work the other way around. So for example, let's say we have a box here, and that box is sitting on some sort of plane, like that. And we're pulling that box, let's say, with a force going in this direction, like that. So I'm pulling the box with that force right here, and this force, since it's a vector, also forms some sort of angle. What I can say with the principle of superposition is that I can act backwards, okay? I can say that this FF is the resultant. So this is the resultant force that is acting on this box. So on this box, I can decompose I can decompose its resultant force into its Cartesian or Cartesian, no, not Cartesian, sorry, components, into its components, okay? That net force, Fr, is equal to the sum of both a horizontal component, so a horizontal vector going in this direction, and a vertical vector going in this direction. Okay? Fy. So this system actually becomes something like this. We have our box, we have our plane, like that. And this force is equal to, this system is equal to one component going upwards, so Fy, so one force trying to move the box upwards, and one force trying to move the box towards the right. So one force is trying to lift the box, and another force is trying to push the box along this side. Okay, so as long as this angle becomes closer to 0, this component becomes bigger and this one becomes smaller. Okay, and just to finish, let's remember that Fy is equal to F sine of theta, and Fx is equal to F cosine of theta. Okay, so since we can work from these two forces into a resultant, we can also have, from a resultant, we can go back into two different forces, the components, the horizontal and vertical components. And this, as we will see later, this will be super useful when we determine in what direction these objects are moving and with what acceleration. So I'll leave that to another video. Thank you for watching. Have a good day, guys.